We know that light imparts force. This is a concept that was intuitive for a long period of time. Historically, a lot of people thought about it. One of the earliest documented pieces of evidence of a discussion related to this can be found in Kepler's writing in his treatise De Comatis, which dates back to all the way 1619 or so. In this work, he was discussing the tails of the comets and their orientation, which were always pointing away from the sun. This, in a way, indicated some kind of radiation pressure from the sun onto the dust surrounding a comet. About 2 centuries later, the first electromagnetic theory of light was formulated by James Clerk Maxwell. He published his famous treatise in 1873. Later on, Heaviside and other Maxwellians uh, formulated the equations in the form that we use today, which is in the differential equation and the integral equations, whatever is coming out of it. This indicated a connection between the electromagnetic field of light and an associated momentum. One of the key aspects of Maxwell theory was to show that the imparted optical momentum was directly proportionate to the intensity of the light that was utilized. Of course, to observe the momentum exchange between light and matter took a very long time. In fact, there were many attempts made. Only around late 1800s and early 1900s, there was some kind of a development in terms of experimental verification of this momentum. This took a long time because the observed effects are difficult to measure due to the nominally low intensity of light sources. And this is a significant challenge even today. You cannot merely just measure radiation pressure by utilizing conventional sources, or for that matter, even sunlight. Because if you want to impart that momentum onto the matter, it would take significant intensity for one to observe it. So, this prospect took a new turn altogether thanks to the emergence of lasers, which are light amplification by stimulated emission of radiation, which are the sources which really play a significant role. And this happened in and around 1960s as an intense light source that could be employed to observe many effects that were otherwise not feasible with conventional light sources. Lasers really played a significant role in bringing out a new form of light source for a variety of applications. Arthur Ashkin took a keen interest in the optical momentum transfer and experimentally showed acceleration and trapping of micron-sized particles due to radiation pressure. He formulated the basic theory of optical forces at the Rayleigh regime, where dipole approximation could be used, and at the limits of geometrical optics, where waves can be expressed or approximated as optical rays. His analysis showed that two categories of optical forces were in play that arose due to gradient of intensity and the Poynting vector S of the electromagnetic waves. These forces are called generally as the intensity gradient forces and scattering forces, respectively. In the last few decades, the structuring of laser light has provided new impetus to explore how the parameters of light can be harnessed in optical micro and nano manipulation. Among the parameters available for momentum transfer, polarization of electromagnetic field and the optical phase have shown significant promise, especially by structuring the optical beam utilized for light matter interaction. The polarization manifests as the spin curl force that has the ability to generate angular momentum related dynamics. It is a very fascinating area which I am hoping to also talk more going in future. In recent years, the optical phase, particularly the optical phase gradient, has been explored in the context of optical momentum transfer. The phase gradient essentially arises due to the transverse component of the momentum flux This was indicated by Rochman 2008, which I'm going to refer to later on. And this is due to the phase profile in certain structured optical beams. For a generalized structure beam, the phase essentially is given by phi, and this has two components, as you can see, the RHS kz as a function of r times z, plus there is a transverse component to this. This indicates essentially the longitudinal phase, this particular term, and the second term essentially represents the transverse component of the optical phase. It is the gradient of this transverse component of the phase that is connected to the transverse component of the optical momentum, G perpendicular. And this G perpendicular essentially is one half of the G, which is the optical momentum flux of the electromagnetic waves. We will discuss this particular connection going forward because the connection between this G and the phi is significant. So is the connection between the G and the polarization at some point of time. So these are the references which I would urge you to have a look at it. The first one is a derivation of Maxwell's equation uh, through the notation of Heaviside. And this is a notation we use nowadays, by the way. And the second one is the optical forces arising from phase gradient, which was one of the earliest papers in 2008 to recognize that optical phase gradients can be connected to optical forces. And this is an important kind of development in the field. And it also tells you why structuring of light is important, and how you can influence the optical forces due to the structuring of the electromagnetic radiation. So hopefully, I'm going to discuss more about this in the coming lectures. And until then, bye bye.